Hey there, statisticians. Mrs. Crum here from Skew the Script. And today we're going to talk about describing a quantitative variable. Let's skew it. Today's lesson is on describing a quantitative variable. Let's jump in. Moneyball is a movie about the Oakland Athletics baseball team, also known as the Oakland A's, in their 2002 season. When the movie came out, it was a big hit. At the box office, it grossed $110 million. However, the wide popularity of a movie about the Oakland A's 2002 season is a bit of a surprise, because in the 2002 Major League Baseball season, it was the Yankees, not the A's, that scored the most runs. It was the Braves, not the A's, that had the largest division lead at the end of the season. And it was the Angels, not the A's, that won the championship. So that brings us to today's key question. Why would anyone make or even watch a movie about the Oakland A's? With that question in mind, let's move into our guided notes. We're going to talk about 3 topics today, starting with dot plots. To get a sense of the movie Moneyball, let's watch a favorite scene featuring Brad Pitt playing the general manager of the Oakland A's. Take a look.
No, what's the problem, Barry?
We need 38 home runs, 120 RBIs, and 47 doubles to replace.
The problem we're trying to solve is that there are rich teams and there are poor teams. Then there's 50 feet of crap. And then there's us.
As the clip makes clear, in professional baseball, there are rich teams and there are poor teams. This table shows all team payrolls from the 2002 season. The payroll for a team is the total amount of money they pay to their players. The payroll, measured in dollars, is a quantitative or numerical variable. The New York Yankees had the highest payroll at $126 million. This means that they could more easily afford to recruit star players to their team. Meanwhile, the Oakland A's had the third lowest payroll at $40 million. With a lower payroll, it's more difficult to attract star talent to your team. We can take this quantitative data and construct a dot plot. The dots show the payrolls of different teams, and teams with highly similar payrolls are stacked on top of one another. The New York Yankees are represented by this dot at $126 million, and the Oakland A's and Minnesota Twins are represented by these 2 stacked dots since both of their payrolls were about $40 million. One advantage to using a dot plot is that we get to see every data value as its own dot, laid out on the full scale of the data. This is especially useful for smaller data sets. There are some disadvantages to using a dot plot to visualize a data set. We can't see each point's exact value. If a dot falls between tick marks on our scale, we have to eyeball its exact value on the x-axis. And because every data value gets its own point, dot plots can be a bit overwhelming to look at for very large data sets, and patterns can be difficult to see. Next, let's take a look at another way to visualize the data, a histogram. Often, we're more interested in summarizing the data than looking at each individual point. So let's go ahead and summarize this data. To do so, we're going to organize the data values into intervals, called bins. Note that it's fairly standard for these intervals to include the lower bound, which means that we'll be using the less than or equal to signs for that lower bound. And it's also pretty standard for these intervals to exclude the upper bounds. So the less than signs on the right side don't have the or equal to notation. We see that there are 2 teams in our data set that fit into the first bin. Note that the A's with a $40 million payroll don't go into this bin since that upper bound is excluded. Instead, they go into the next bin where $40 million is included, and there are 12 teams. And we can fill in the rest for a total of all 30 teams captured from our data set. It's worth noting that only 1 team had a payroll in the highest interval, the New York Yankees. Using our table, we can now construct a histogram. We're going to use the x-axis to represent the variable we're measuring, the team payrolls. And we're going to use the y-axis to represent the frequency of different payroll values. When we do that, this is what we get, a visualization of these bins known as a histogram. You might notice that it's somewhat similar to a bar graph. However, unlike a bar graph, there are no spaces between the bars, indicating that we are visualizing a quantitative variable here, rather than a variable with distinct categories. It's important to make sure you label your histogram so that people can make sense of it. We've already seen how some graphs can be misleading. Taking the time to provide the labels avoids that confusion. The best way to read a histogram is to look at the bar heights. For example, we see that 80 to almost 100 million has a bin height of 4. This means that 4 teams have a payroll between 80 and almost $100 million. It's important to note that the height of the bar doesn't indicate that these teams have higher or lower payrolls. In fact, the highest payroll team, the Yankees, are represented by the bar with the lowest height. The height of the bar merely represents the number of data values, or frequency of the data values, in a certain interval or bin. In this case, only one team, the Yankees, fit into this very high bin. In addition to looking at the frequencies of data values in these bins, we can also look at the relative frequencies or proportions. For example, we saw that there are 2 teams with payrolls between $20 and almost $40 million out of the total of 30 teams. We can represent this relative frequency by dividing 2 by the total of 30, which yields a proportion of 0.067 or 6.7%. So 6.7% of teams have payrolls between $20 and almost $40 million. Similarly, there are 12 teams in the next bin. Out of the 30 teams, this yields a proportion of 0.40. So 40% of the teams have payrolls between $40 million and almost $60 million. And then we can do the same for the rest. Note that for relative frequencies, the total should be 100% to represent all teams. We can take these relative frequencies and construct a relative frequency histogram. It looks basically the same as the raw frequency histogram we had earlier, but now the y-axis represents the percent or relative frequency of each bin. So the bar heights tell you the percent of the data set contained within a certain bin. The key advantage of histograms is that they're great for summarizing large data sets, as the bins help to group the data, making patterns easier to see. However, the largest disadvantage is that you can't see individual data values. Instead, you can only see an interval that contains those exact values. Now we're ready to think about how to describe a distribution. To describe what you see in the data, what features do you need to talk about? To give you a way to think about this in multiple situations, we're going to use a strategy consistently throughout this course, starting with the big picture and then zooming in on the details. To describe a distribution, start with that big picture, looking at the landscape. That's the context of the data. Next, take a closer look. What's the data look like overall? What's the shape and the spread? And finally, zoom in close. What does the data look like in detail? That's where you describe anything interesting or unusual about it and talk about the center, like the mean or the median. When describing shape, you can comment on the number of modes or peaks. If a distribution has no prominent peaks or modes, we say it's approximately uniform, meaning that the frequencies are uniform or similar all across the data values. If a distribution has one clear peak or mode, we say it's unimodal. Finally, a bimodal graph has 2 distinct peaks or modes. Another important aspect of shape to describe is symmetry or skew. If a distribution has a tail on its left, it's called a left skew or a negative skew. A tail on the right indicates a right skew or a positive skew. And the distribution in which each side is roughly the mirror image of the other is considered symmetric. Now, you may have noticed that the word skew appears in the name of our organization, Skew the Script. This is no accident. As educators, we notice that when we use the usual script for teaching math and statistics with irrelevant examples like Bob having 58 watermelons or calculating the mean lifetime of batteries, student scores look like this, a right skew. Many low scores on the left and only a few scores that were high on the right. However, when we went off script and used math and statistics to explore genuinely relevant topics that students cared about, students engaged more in class and they performed better as well. As a result, their scores became a left skew. Very few low scores on the left and many high scores on the right. That's why this left skew curve appears in our logo. It's a symbol of what we hope to accomplish by bringing more genuinely relevant examples to math and statistics classroom. And it's what we mean when we say, let's skew it. So now we have tools and a strategy to describe this distribution. Starting with the big picture, we want to tell what the context of the data is. This data is about baseball team payrolls in 2002. And now we can take a closer look to consider the shape and the spread. Since the values go down to almost 20 million and as high as 140 million, the spread is quite large. And if we draw a curve around the histogram, we can show that the distribution is skewed to the right, meaning that most of the values are on the lower end. Finally, we zoom way in to really explore what is happening in the details. Over half of the team's payrolls fall into the $40 to $80 million range, with the center falling somewhere between 60 and 80 million. So that's the whole story of this distribution. It's about baseball team payrolls in 2002. The spread is quite large and skewed to the right, with over half the team's payrolls falling into the $40 to $80 million range, and a center between $60 and $80 million. By starting with the big idea and gradually zooming in on the details, you can give a good description of the data. Now that we've done so much work with this data, let's get back to our key question. Why would anyone make or watch a movie about the Oakland A's? As we saw before, the A's had a much lower payroll than the wealthier teams such as the Yankees. To make up for this deficit, the A's had to develop a strategy, and that strategy is best explained by another favorite scene from the movie.
It's about getting things down to one number. Using the stats the way we read them, we'll find value in players that nobody else can see. People are overlooked for a variety of biased reasons and perceived flaws. Age, appearance, personality. Bill James and mathematics cut straight through that. Billy, of the 20,000 notable players for us to consider, I believe that there is a championship team of 25 people that we could afford, because everyone else in baseball undervalues them. Like an island of misfit toys. Billy, this is Chad Bradford. He's a relief pitcher. He is one of the most undervalued players in baseball. His defect is that he throws funny. Nobody in the big leagues cares about him because he looks funny. This guy could be not just the best pitcher in our bullpen, but one of the most effective relief pitchers in all of baseball. This guy should cost $3 million a year. We can get him for $237,000.
The A's were one of the first teams to use advanced statistics to identify undervalued players. In other words, effective players that they could afford. The result was that even though the distribution of team payrolls looked like this, the distribution of wins per team looked like this. The Yankees, as you may expect, won an impressive 103 games during the season. However, the Oakland A's, with their payroll being a fraction of that of the Yankees, also had 103 wins. They somehow tied with the Yankees to have the best record in baseball that season. To put this in perspective, this means that with their payroll, the Yankees spent about $1.2 million per win. Meanwhile, the A's only spent $0.4 million per win. Quite an impressive feat. So now that brings us to our discussion for the day. Major League Baseball has a luxury tax. Rich teams pay a tax to the league, and the revenue is used by the league to help fund poorer teams. However, the poorer teams say that the tax isn't big enough to make much of a difference. Imagine that the league enacted a harsher and bigger tax in the 2002 season, the same season from the movie and from the data we collected. Any money spent above $100 million on the payroll is taxed at a 90% rate. So 90% of that money is taken by the league and given to the poorer teams. This leads us to two discussion questions. First, how would this change the distribution of team payrolls? In your answer, you'll want to comment on shape, spread, and center. And then secondly, in your opinion, would this new system be better for the sport? Why or why not? Take a moment to jot down your initial thoughts to these questions to discuss them more in class. That's it for today, statisticians. We'll see you next time.